Welcome everyone to today's webinar. The 12th in our series of Transparency is the New Green in Product Selection and Specification. The reason we're having this webinar is to celebrate and announce that CIMA and CIMAC, the Cellulose Insulation Manufacturers Association and Cellulose Insulation Manufacturers Association of Canada, have completed and we are delivering the very first industry-wide EPD or loose fill cellulose insulation, which is a carbon storing material. And there's a lot of information just packed into that statement. And so we're going to spend some time today unbundling all that's packed in, but a lot of information. So if you have questions, please put them in the questions panel, and we'll take some questions at the end. Any questions we don't get answered, we'll follow up with you to answer. This is being recorded. It will be made available to you. We'll send you the link in the follow-up email. And if you would like the deck, you'll be able to request that, and we'll send that out to you as well. So starting with this phrase, transparency is the new green. When we launched the Transparency Catalog in 2016, it was with the insight that the new credits in the green building rating systems rewarding manufacturers and project teams and owners who were specifying products with environmental product declarations and material ingredient disclosures had raised the bar permanently to say, look, if you're going to be making environmental and material claims, you have to be using real scientific methods that we're all agreeing to use the same way, the same structure to get ultimately comparable and consistent results. And so the purpose of this webcast series is actually the opposite of a CEU course. It's expressly for those manufacturers who are committed to making higher performing, greener and healthier products to come on and tell their stories about what they're actually doing so that the data in the EPDs and material ingredient disclosures can start to make sense. They can bring that information to life. So today, we have a little bit of a really special guest with Chris Magwood, because it became really clear that to talk about the significance both of an industry-wide EPD for cellulose insulation and just the importance of cellulose insulation being a biogenic material, and now with this really increased focus on embodied carbon, having Chris with us today is going to put the whole story in context. And I think you're going to be really excited to learn about the work that he's done, developing models and strategies to be able to compare approaches for traditional buildings, buildings traditionally, and now with an eye towards an intent towards getting to net zero carbon. Then I'm going to show you a quick overview of the industry-wide EPD, our transparency report is what we call our EPDs, how to access all the manufacturers who have participated, because again, at the end of the day, it's about actually specifying higher performing materials, getting those into the spec, getting them into the building, so being easy to find all those manufacturers who are making this product. Dan is then going to give you a really great overview of what is cellulose insulation, how is it made, what are the primary applications, and then I'm going to do a live demo of how to use the Transparency Catalog, the CIMA-CIMAC listing, access to the EC3 tool, and to the participating manufacturers. So a little bit about folks who are on the webinar today who are not familiar with Sustainable Minds. We're a software company. We started in 2007. I'm Terry Swack, the CEO and founder. We have always been focused on delivering easy-to-use tools for product manufacturers, and now architects, engineers, and contractors to understand life cycle assessment and technical environmental information to be able to use to make better informed decisions, both in product manufacture as well as in now in product selection for buildings. We are the only end-to-end product transparency solutions provider in the market today. We're a program operator, so we do PCR and EPD development, which I'm going to show you. We also deliver LCA and material evaluation services, which we feel is a pretty important requirement to be in this space. You have to be delivering the technical services to really understand all of the implications of every decision that goes into creating an LCA or a disclosure, and ultimately to informing how to write good PCRs and rules for Type 3 environmental declarations. And we've developed this innovative cloud platform to make it really easy for people looking to select and specify products from manufacturers who are investing in product transparency, to make it easy to find every manufacturer doing so in every master format, division, and section, and to be able to do it in a click. And we'll show you that when we get to the demo too. Here's really kind of our big picture idea, which is that we believe that product transparency does build credibly greener brands, but not by just producing disclosures. That the value for manufacturers to provide environmental information about their products comes from demonstrating they understand what it means and they know what they're doing. Because ultimately, to make better decisions, you need more consistent, understandable, and meaningful information. And when a manufacturer provides that, they're providing truth, which should build trust, and trust builds powerful brands, and powerful brands create preference and value for their companies. So with that, I'm going to turn it over to Chris and take it away, Chris.
Okay, thanks, Terry, and thanks to everybody who's participating out there today. I'm going to talk about the potential for climate change solution in low and mid-rise buildings. Just a very quick background on myself. My name is Chris Magwood. I have run a design build firm that's how I started my career 25 years ago. And currently I wear two hats. I'm the director of the Endeavour Centre, which is a sustainable building school up here in Ontario, Canada. And I'm also the director of the newly formed Builders for Climate Action. And a lot of the information I'm going to share with you today is from a study that I did for that group. So in this presentation, I'm going to be looking at sort of the two ways that buildings impact climate change. One, the upfront embodied carbon emissions is sort of starting to get talked about now, but is not really that widely understood or widely applied yet. But it's all the emissions associated with harvesting, transportation, and manufacturing of building materials. And it's measured in kilograms of carbon dioxide equivalent. And a lot of that is the information that you're going to find on the CIMA EPD for cellulose. And then, of course, the part of building emissions that lots of people in the industry have been working on for a long time, which is the operational side of things, which is the amount of energy being used in the building multiplied by the emissions from the energy source. And so this presentation will sort of look at how all of that combines to present an overall carbon footprint for the whole building. Another concept that we're going to be sort of addressing in this presentation is materials that are a carbon store. And this is something that certainly has not been on the radar in the building industry very much. But essentially, it's looking at plant-based building materials. So as a plant grows, and that plant could be a tree, the plant could be rice, the plant could be bamboo, the plant could be cork. But as that plant grows, it's absorbing CO2 from the atmosphere and using it both to build carbon in the soil, but also to make the structure of the plant itself. And then when we turn those materials into building products, there are emissions associated with harvesting and manufacturing them, so cutting them, processing them. And to figure out whether there is net carbon storage or not, we're basically taking the amount of CO2 in the plant, the amount of carbon in the plant itself, subtracting the emissions that happened while making it into a product, and seeing if the balance is negative or positive. If it's negative, it means that material has an amount of carbon stored in it that otherwise would have gone back to the atmosphere. But if we're putting it in a building, then we're able to capture that and take it out of the carbon cycle. And so we would call this a carbon sink. And what the whole study sort of adds up to is embodied on this chart, where business as usual will result in buildings having quite high upfront carbon emissions, fairly high operational emissions, and so having a total carbon footprint that sort of on a per square meter basis is extremely high. Or we'll be looking at how we can make a building that actually has net carbon storage when the building starts, and how you can operate it efficiently with clean energy so that in the next 30 years, it's still effectively a carbon sink rather than contributing to climate change. So in order to figure out how we do that, first we'll look at the upfront embodied carbon emissions side of things. And so I did a study for my master's thesis last year, in which I looked at 8 examples of 2 different types of low-rise buildings, a single-family home, a raised bungalow of about 2,000 square feet, and then an 8-unit, 4-story multi-unit residential building of about 10,000 square feet. And I assembled environmental product declarations from all the materials that you could possibly make these buildings out of. And what I found quite quickly as I sort of assembled all those EPDs was that in every category, whether I was looking at foundation materials or insulation or cladding or flooring, that the materials tended to group in themselves pretty conveniently into 4 kind of categories. There were those that were sort of at the high end of the spectrum, a bunch in the middle, a bunch that hovered sort of right around the 0 carbon footprint level, and then some that had a lot of storage, carbon storage built into the heavily biogenic building materials. And so from all of the materials I gathered, I sort of made 4 model buildings that followed those typologies. So a high, a typical, a best conventional, and a best model. And so what we'll do is we'll sort of just very quickly, not going to spend too much time looking at each of the materials and categories, but you can see that as we build the building from the ground up, foundation, slab, walls, cladding, etc., all the way through the main enclosure and key finishing materials, that materials that were sort of clustered at the high end of the embodied carbon range, that 10,000 square foot multi-unit building, just in making and manufacturing the materials, you'd have about 212 tons of emissions associated with that building before it begins to operate. So this is its upfront carbon footprint is 212 tons. If I assemble the exact same building with all the same performance specs, but I'm sort of choosing now materials from more of the mid-range of all the EPDs I collected, that exact same building has reduced its carbon footprint upfront to 68 tons. So a pretty dramatic decrease in the carbon footprint simply by some really simple material substitutions that were able to drive that embodied carbon number quite a bit lower than the one on the left. The next model I assembled was trying to take the absolute best materials from what's available widely and used conventionally and is code compliant right now. And so as we build up that building, this is the first time we come to a negative number. So you can see when we get to the walls And here's where the cellulose insulation comes into play, as well as the wood fiberboard insulation that's on the outside of this particular building model. The negative number means that those materials had net carbon storage. And so, as I sort of described earlier, the negative number that reflects carbon stored in the materials comes from materials that are plant-based and that are basically storing carbon that would have otherwise gone back to the atmosphere. So in the case of cellulose insulation, that recycled newsprint, if the newsprint wasn't made into cellulose, it would probably have either ended up in landfill or potentially being burned, in which case all the carbon stored in it would be back in the atmosphere. But we've interrupted that cycle by bringing that material into a building for, depends on the lifespan of the building, but safely anywhere from sort of 30 to 100 years, and essentially remove that carbon from the carbon cycle. And so, we're talking in this webinar about cellulose, but there are lots of plant-based building materials, some of which, like cellulose, have been around for a long time and are sort of well established in the market and available and manufactured widely, and others that are equally as accessible, and some that are much less accessible, that have been used in a sort of limited way, or that are in the R&D stage, or that are just sort of coming onto the market now. But all plant-based materials sort of have this net carbon storage. And so you can see, if we go back to this building typology, if we add some carbon storing in the FSC wood on the floors and in the cladding and in other parts of the building, that now this exact same building is at minus 15 tons of upfront embodied carbon. So we've now switched this building from being quite a major contributor to climate change at the 212 to a reduced amount of upfront carbon at 68 tons to this yellow typology that is sitting just below the zero line at minus 15 tons, which is pretty remarkable given that we haven't really adjusted the cost of the building or the difficulty of the building or the constructability in any way to make that big an impact. And then the final building I modeled was to look at using materials that were sort of best in category, regardless of whether they were widely available or widely accepted, but they're all feasible. They've all been used to build code-approved buildings in North America. My threshold was I had to be able to find 10 examples of a building in North America that had been code-approved with these materials. And in the best case scenario, the net storage has gone all the way to 117 tons. So in other words, almost a complete paradigm reversal from the red and the blue typologies. We now have a building type that's storing a really significant amount of carbon overall. I also modeled these buildings. The model I just ran you through, those figures are for meeting Ontario's code minimums for energy efficiency. And I also modeled the exact same building as though it was meeting the net zero ready codes that are coming in Canada, I think in 2025, if the government sort of sticks to its promise. And so one interesting thing that happens as we made the buildings more energy efficient, if we're using insulation products that have a lot of embodied carbon associated with them, if they're responsible for emissions in the creation of those insulations, we're actually driving the upfront emissions of the building up in order to try to drive the operational emissions down. And the exact opposite happens when we insulate with biogenic materials like cellulose. When we add cellulose insulation, we both make the building more energy efficient and we're storing more carbon up front. So you're kind of getting a win-win out of that scenario. So instead of having to make up for a deficit that you've created by using a more intensive insulation, you're actually just increasing the storage in the building before you start operating it. And so that's the kind of spectrum that I ended up with at the end of the study. At the high end, there was 241 kilograms of CO2 per meter squared of building. And at the best end, it was storing 137 kilograms per meter squared. And I think the really sweet spot is that yellow typology building, and that's the one where cellulose really played the key role in sort of making the difference there in bringing that building down to be a zero emissions building. And just to give you a sense of what that means, if we look at buildings across this sector, we were just looking at one building there, but if I were to build everything that's built in the US in those two building typologies, so low-rise residential buildings, if they were all built in this sort of that red typology, it would be the equivalent of adding 15 coal plants worth of emissions to the atmosphere every year in the US. So 54 million tons of emissions just from the materials and making those buildings. And if we were to flip things around and be able to do things in the best possible way with lots of biogenic materials in the buildings, we wouldn't make those 15 coal plants worth of emissions, and we'd additionally remove the emissions of 10 coal plants. So at scale, this kind of approach to building by filling the buildings up with biogenic materials could have a really dramatic effect on our climate concerns. So that was the upfront embodied carbon emissions. And now those same buildings we'll look at through the lens of their operational emissions and kind of see how those two things might balance out. And so it's the same two model homes. Again, one always done in the code compliant, code minimum standard, and one done to a net zero ready standard. And those are all the R values that were used. And this is based on Toronto, Ontario climate data. So again, you know, the results of this study would be different in different scenarios. So here we've got the operational emissions using natural gas for heating, which is pretty common in our part of the world and around North America. And so these buildings would be adding about 300 tons or 10 tons a year between now and 2050. And so you can sort of see with each of those building typologies, what happens is, you know, that 300 tons is being added to the total. But what's interesting is with the yellow and the green typologies, because they started in a negative number, by the time you've emitted those 300 tons of emissions over 30 years, you're actually less than 300 tons. Okay, my time is up. I just wanted to quickly show you that the reductions from making the buildings more energy efficient are actually less than the reductions from reducing the embodied carbon of the materials. And that the same thing applies if we move to electric heat pumps, where we've greatly reduced our emissions from natural gas. We can now build and operate the buildings in the different typologies for less carbon than just making the building on the left side of the spectrum. So I will.
You can take a couple more minutes to wrap up, Chris.
Okay, these last couple slides. So what I really wanted to sort of point towards is, you know, using biogenic materials like cellulose to look at a different type of metric for the buildings, where we would look at carbon use intensity as the sum of the upfront embodied carbons and the operational emissions, so that depending on your climate, your building type, the types of materials available to you, you're actually, you know, working with a metric that is looking at the overall carbon intensity of the building and not just the energy efficiency of the building in the end. And that as governments, here in Canada, our government has committed to being carbon neutral by 2050. That essentially means we need to have a carbon use intensity that's zero by 2050. And that, you know, there's a sort of stepped pathway towards getting there, and that, you know, that yellow typology building, the one that already kind of gets us to a zero embodied carbon, did rely heavily on cellulose insulation to get there. Other great things, and I think these will be touched on later in the presentation, but there are all kinds of stacked benefits from using biogenic materials. They're healthy, they're more regionally produced, they're equally affordable compared, and sometimes even less expensive than their competitors. And I'll just go through some case studies. of some buildings that we've built at our school. And I'll draw your attention to this one in particular, which is heavily filled with cellulose and manages to surpass even the best results from the study, so that it's storing 250 kilograms of CO2e per meter squared. And yeah, there's a huge difference in what we can achieve between what our sort of current practice is and what best practice could be. And looking at using biogenic building materials is how we will get there. And sorry for going a little long, but that's what I had to present.
Hey, Chris, no problem. And what you're sharing is really important and probably pretty new to many of the folks who have come today. So again, if you've joined us a little bit later, both this recording of this webinar will be made available, as will the deck if you request it. So moving right along, I'd like to introduce Dan Lay, the Executive Director of CIMA and CIMAC, to tell you about cellulose insulation and its applications.
Okay, let's see if this is working. Yes, it is. Thank you. Well, thank you, Terry, and Chris, thank you very much for this fascinating presentation. I have learned a lot since I've been exposed to your work, and I think it's very important, and it's a great contribution to the building industry. I am, as Terry said, I'm Dan Lay. I've been around the insulation business for quite a number of years on the staff of various insulation industry associations. And I currently am the executive director of the Cellulose Insulation Manufacturers Associations of the US and Canada. Cellulose insulation is produced from recycled paper fibers, either paper, as we think of paper, or cardboard, like the material that Amazon ships things to you in. And the balance is fire retardants. We think it's a simple idea. We think it's a better idea. And I leave it to people that are looking at the facts to determine whether it's a greener idea. The one thing it isn't is a new idea. Cellulose insulation as we know it today has been around since the 1920s. I know I often see people who probably should know better writing, oh, cellulose insulation started in the 1970s. No, it's much, much older than that. It's been time proven over about well over 90 years. The oldest member of our US association has been in business and making cellulose insulation since 1949. Well, the production process starts when somebody recycles paper. Logically enough. Now, some of that is made into new paper. Unfortunately, a lot of it ends up in landfills or incinerators where it does nobody any good, and in fact causes a lot of environmental damage. But some of it, about 1 million pounds a year, goes to cellulose insulation plants, like this one in Georgia, where it's converted into energy-saving building material. And here is paper in a raw material warehouse ready to be converted into cellulose insulation. Oops, excuse me, I hit the wrong button. The production process starts when the paper is loaded into a mill that first cuts it to pieces that are about the size of a typical human hand. During this process, there's an electromagnet that removes contaminants like staples, paper clips, and believe it or not, one of our members actually pulled a gun out of a bale of recovered paper. So. In the final stage, the paper is reduced to a form that really resembles the original paper mill, paper pulp rather, and it's done in a mill that uses rotating discs and a blast of air to reduce this material to fibers, and at the same time the fire retardants are added. Once the insulation is produced, it is compressed into a brick that is subsequently wrapped in packaging and ready for shipment. Now, this is kind of an interesting packaging system, that this actually compresses the insulation into the brick before the packaging is applied. In most cases, as soon as the insulation comes out of the bagger, it goes right into a truck to be shipped out to home centers, lumber yards, contractors. And one of the worst jobs I can imagine in American industry are the people that are sitting at the other end of that conveyor belt there, grabbing those bags as they come down the line and loading them onto the truck. But it's a fascinating process to see how rapidly these trucks are filled with this insulation. Obviously, there are standards that the products have to meet. In the US, there's the CPSC standard, it's a Consumer Product Safety Commission standards, and there are also 3 different ASTM standards that apply to cellulose insulation for various applications. In Canada, the material must meet the federal government standards, as well as the CAN-ULC National Standard of Canada for cellulose insulation. Now, to assure conformance with these standards, testing is conducted throughout the production day. On the picture on the left is a device called a radiant panel. What this does, it subjects the surface of the insulation to a radiant heat flux. The insulation is then ignited, and the flame front across the insulation is measured. And from that you can calculate what's called the critical radiant flux of the material. So that's done, typically it's done almost constantly throughout the day. As soon as you complete one test, the other one starts. There is also a test for smoldering combustion. That's shown in the picture on the right. And what happens there is an ignition source, traditionally a Pall-Mall cigarette, but now a NIST standard reference material is inserted into the insulation. And after any smolder completely extinguishes, it's weighed to see how much material or how much weight has been lost. Well, Chris, from Chris's presentation, I think we have an idea of one of the reasons for cellulose insulation. Certainly, it's its carbon storage potential. But cellulose, even the competitive products of cellulose agree that it is the lowest embodied energy. That is, R for R, it takes less energy to make cellulose insulation than to make any other insulation material on the market. It has the highest post-consumer recovered content, and that is, there's no disputing that. Although some materials, some of our manufacturer members have agreements with printing plants, particularly large newspaper printing plants, to take their overissue and their material scrap. And that, of course, is not post-consumer, that's post-industrial. There's absolutely no waste generated on the site when the material is used. Any overspray, anything that is excreted off is vacuumed up and reused. Cellulose insulation plants are scattered throughout North America. Obviously, in the sparsely populated western states, they're farther apart. But here in the Great Lakes area, where I'm from, there's probably a cellulose insulation plant. You're probably never more than 150 miles from a cellulose insulation plant. And in the same vein, much of the feedstock, the paper material that's used in making cellulose insulation, is recovered locally. So you don't have to ship the material very far in most cases, and you don't have to ship your raw materials very far. Once the material is installed, it results in high energy savings for homeowners. And then this, getting back to the subject of our webinar today, it is a carbon sink that traps the carbon in the walls and attics of homes for the life of the building. Just a quick look at some of the benefits of cellulose insulation, which we've already alluded to. Excellent insulation properties. The latest information we have from Oak Ridge National Laboratory is that at a installed R value of R48 in an attic, the R factor of cellulose insulation is about 3.8, which is fairly high on the scale of residential insulation materials. Interestingly, and a lot of people don't understand this, cellulose makes walls more fire resistant than any other insulation that's commonly used in residential construction. We have, again, low embodied energy, high post-consumer recovered content, paper redirected from landfills, and trapping carbon in the walls for years. Now, we should understand that looking at the big picture, there are basically two forms of cellulose insulation. The conventional or standard loose fill material, which is the subject of the transparency report, and material that contains adhesives. So the transparency report doesn't apply to the materials with adhesives because the adhesives haven't been figured into that. So we're going to be talking for the next couple minutes here about the conventional loose fill cellulose insulation. And obviously the first thing you think of in terms of insulation is energy savings, thermal insulation. But cellulose insulation is also very good as an absorptive material in wall and ceiling assemblies as far as soundproofing buildings. So one of the very common uses of it is for acoustical purposes, particularly in say motels or in party walls, anything where you want to muffle the noise and reduce noise transmission. So I mentioned that cellulose makes some of the most fire-resistant walls you can build in residential construction. And in the picture there, you see kind of a hokey little demonstration that we've been doing for years using a blowtorch and a handful of cellulose insulation and melting a penny using a blowtorch. Now, don't try this with any other of the common insulation materials because you're going to get a very serious burn in your hand if you do. Cellulose virtually any wall with cellulose insulation is a 1-hour firewall. And several of our members have qualified 2-hour firewalls and some even 3-hour firewalls. In the building code, cellulose is approved as a fire blocking material, and it is also has been tested and qualifies as a fire stop material for around steel through penetrations. So the material has very good fire protection properties. Now, we don't really test the insulation by using a blowtorch. This is how the how the fire resistance ratings are determined. It uses an ASTM E119 test instrument. The picture you see there happens to be a wall at the National Research Council of Canada Fire Laboratory, just ready for testing. After that wall was tested or burned, as we say, that show had fire resistance of 132.2 minutes, which of course is about 15 minutes longer than a 2-hour firewall. An identical wall with rock wool didn't quite make it to 2 minutes. Okay. Okay, now we're looking at two of the most common applications of cellulose insulation. It's blown onto attic floors, and it is packed into wall cavities that are closed using webbing or netting, or you can even install the drywall and blow it behind the drywall. Spray application of cellulose insulation uses a little water add-on that makes it adhere to the wall. Now, some spray products have adhesive in them, others do not. So the applicability of the transparency report depends on whether you have a material that has the added adhesive, or whether or not it just uses a little water mist to activate the adhesive properties of the material itself. Once a wall is sprayed, its material is screeded off there. But as I said, there's no waste. So while that person is screeding off the material to stud face level, there is another person there with a vacuum that is sucking it all up and taking it back to the blowing machine to be installed in the next cavity. And that's what a finished sprayed wall looks like. Cellulose insulation can also be installed in netted cathedral ceilings, such as we see here. There are also commercial applications for cellulose insulation. Now, this material, this is a special type of material that does contain adhesive, so it is not covered by the transparency report. And it's used for fire protection, acoustical purposes, decorative purposes, and for thermal insulation. You frequently find it in auditoriums, exhibit halls, metal buildings, arenas, gymnasiums. And here's some examples. This, the red ceiling you see there in this pizzeria is cellulose insulation. The ceiling you see in this hotel lobby is cellulose insulation. The overhead deck in this parking garage is cellulose insulation. And we can't see it here because it's up above that the superstructure there, but the roof of this sports arena is coated with cellulose insulation. Chris has given us some very good information about the benefits of cellulose insulation as a carbon sink and reducing the carbon footprint of buildings. We've been preaching this story for many years, since the early 1990s. The Cellulose Insulation Manufacturers Association contributed or provided the insulation for the National Association of Home Builders Research Conservation House back in 1993. In 2010, we provided the installation for the National Association of Home Builders New American Home Demonstration House. Kind of interesting, the Resource Conservation Research House was the subject of stories in Popular Science and the Smithsonian Magazine. The Popular Science story was headlined, "The House That Junk Built." The Smithsonian labeled their story, "Would you live in this dump?" The concept of a carbon sink building isn't new. We tried to start promoting that with the New American Home back in 2010, and now it seems to be getting traction. That obviously the work done by Chris's people will have had a big part in doing that. A number of European agencies have promoted the carbon sink benefits of plant-based materials. So we think that the idea that we first put forth 10 years ago is now beginning to take hold. Repeat the benefits of cellulose insulation. I don't want to beat a dead horse here because we've heard them all before, but they do bear repeating because I think it's very significant. And finally, I believe that there'll be a forum for submitting questions. I will certainly be happy to answer any I can. If any of you have questions that aren't answered today, you may want to take note. You can visit us on our website. You can call the association or send email to us. And I thank you very much for your interest and for your attention today.
Well, thanks, Dan. There actually are a couple questions that have come in, and I'm going to pose them to you before we dive into taking a look at the transparency report and the CIMA CIMAC listing. And of course, people can contact you through your listing in the transparency catalog too, so no reason to scramble to write this information down. So the question I've heard you answer before is, with the decline of newspaper in favor of electronic news, is it becoming difficult to source cellulose material for the operation of the plants?
That's a question we frequently get. And to date, there has not been a fiber shortage, because as the number of newspapers have decreased, the shipping materials have increased. As long as Amazon keeps sending out packages by the tens and hundreds of thousands every day, there's going to be feedstock for cellulose insulation.
All right, thanks, Dan. Next question. Are the fire retardants typically halogenated or organohalogen flame retardants containing chlorine or bromine bonded to carbon? Or the FR typically an inorganic material?
No, none of the suspect fire retardants are used in cellulose insulation. The common fire retardants are boric acid, which of course is also used as eye wash and it's frequently found in contact lens solutions. Borax, which is the common name of sodium pentaborate, and that's used to wash clothes. And then there is also, in some formulas, use a material called ammonium sulfate, which is a food preservative, and it's used as a soil amendment to adjust the pH of soil. Those are the common fire retardants in cellulose insulation.
All right. Well, there you have it. So let's take a look at this demo. And for those of you who have not seen the transparency catalog yet, it's designed to be both an educational marketing and sales enablement solution for manufacturers to help them get their stories out, but also to have easy access to all of their sales reps, customer-facing people, distributors, partners, knowing where all their documentation is in a click, being able to provide access. It's free to use, no login, and the same for anyone in the industry coming to the transparency catalog. It's free to use, there's no login, and it's really easy to find manufacturers in any master format, division, and section with transparency information in just one click. So I'm going to jump out here to this demo, and I'm going to show you, this is the transparency catalog listing for CIMA and CIMAC, and as Dan mentioned at the beginning, he is the executive director of both organizations. And what this means is that because both organizations, members of both, participated, this transparency report, which is what we call our EPD, so this is an industry-wide EPD, is for all of North America, not just the US and not just Canada. The way that you can get to this listing is a couple of ways. Because it was just launched, there's a logo right here on the side that makes it easy to get to, or every single manufacturer in the catalog is alphabetically displayed on the front page. This will take you to their websites. You can call them, so of course you didn't need to write that down. Let's focus in here, because this is where the action's happening. Just so that you can see, we'll come back to this. These are all of the participating members. Here's some of the PCR and the benchmarking guidance. But let's dive in right here. Here's how you can get to the industry-wide EPD, or we call our transparency catalog. All the content is available on 3 web pages. So here's the description of the product. Here's the image that was selected. They were very proud to have the NAHB feature, cellulose insulation. Here are all of the participating manufacturers. So from the listing and from the transparency report, you're able to go to any one of those participating manufacturers listing in the catalog and be able to find not only their product information about that particular product, but all of the other products that they have as well. You can learn more about them, contact them, and learn more about their other products. So you can see here's the same transparency report. And on the front page, you've got the dashboard, features and functionality, kind of a shorthand of what Dan told us about, what makes it better from an environmental materials perspective, all the certifications and ratings. And here at the bottom, you can see all of the verification that happened so that you can be certain it is a Type 3 environmental declaration. You can get to the PCR, you can download the publicly available LCA report. Here on page 2 is all of the LCA information, and I'm going to bring your attention to a few of these pieces of content. On the left side of the page is the technical requirements from the PCR of disclosing the application, the functional unit, the data reporting periods. But what we did specifically, and again, this is the very first industry-wide EPD that was created to be a category benchmark to which product-specific EPDs can be compared. So if and when any manufacturer who participated in this industry-wide EPD wants to create a product-specific EPD, they can, and they can compare it directly to this particular EPD. And there's guidance for how that's done, and I'll show you in just a minute. What we've also done is, so we've talked about that here. What we've also done is talked about the uncertainty analysis that we did to understand the range of differences between not only the data that was provided, both from the inputs as well as the percentages in each life cycle stage. We did this uncertainty analysis. The PCR calls for selecting 3 impact categories that will get used in a comparative result. These are them, and so here's the result of that uncertainty analysis. And on the right side of the page is the explanation of what's causing the greatest impacts. This is what people want to know, what was learned from the LCA. And so what was learned is that the greatest impacts are happening in the manufacturing phase. But as we pointed out, because cellulose insulation doesn't require a lot of energy to make, nothing needs to be melted. The production lines can be turned on and off when something's being made versus other types of insulation that are made in facilities where the furnace is running 24/7 by 52. Here are all the results. You can get the background report, as I mentioned, access to the PCR. And then for anyone who did not attend this webinar, on page 3 is you're going to find some of those key stories that Dan talked about today about what's happening in any or all of those life cycle stages contributing to the performance improvements that Dan and Chris both spoke about. I'm going to bring your attention back to the listing. Again, you'll be able to find any of these manufacturers who participated both here in the listing, as well as from the front page of the transparency report. You're going to see here that the carbon footprint, as reported in EC3, shows that cellulose insulation is within the 20th percentile of all products with EPDs in the EC3 tool. And if you haven't had a chance to look at this before, this tooltip compresses the entire EC3 methodology explanation into a tooltip and explains how to read the comparative result that's displayed on the EPD page in the EC3 tool. So what you're going to see here is you can go directly into the EC3 tool. If you haven't set up an account, what you'll encounter when you click there is a login screen, so you can set up an account. But if you have an account, you'll be able to go directly. And what you're going to see here is that here's the results of the industry-wide EPD. This is the actual result that's been reported, that black line. The fuzzy stuff is the amount of uncertainty that's been calculated by the EC3 tool, but because we did an uncertainty analysis in our transparency report, we've dramatically reduced the amount of uncertainty, so that doesn't need to be applied here in the EC3 tool. And you can see that the embodied carbon in the cellulose insulation is well below the CFL baseline and really at the bottom of the range of insulations in 0720, thermal and moisture protection, specifically in blown-in insulation. So that's in the blown category. We're at the top of the hour. I'm sure there's a lot more we'd like to share with you, all 3 of us, but again, I want to thank you for spending time with us today. It is Martin Luther King's birthday, a holiday in the US, but not in Canada. So we want to thank all the US participants and, of course, the Canadian participants. And I invite you to leave your comments on the way out and look for the link to the webinar and share it, tell your friends, and go ahead and access that transparency report and read about and then select and specify cellulose insulation. So thank you, Chris. Thank you, Dan. And I wish everybody a great day.